All right, good afternoon, everybody. All right, so I want to go over a couple quick things before we dive into the review problem. So lecture 4, it's available on Sakai, so you can go on there. I think you have the general idea of where to find them. Couple quick comments. If you downloaded the lucky.cpp file early, you can just delete the period from the 2 print statements and it will match the script test. Otherwise, I've changed the directions such that most of you should be able to avoid that issue. The second thing, based on some of the feedback from the post I had made on Sakai, on Wednesdays at 3:30 p.m., I'm going to have an exercise with the Pupfessor. If you want to meet up in front of my office at 178 Fitzpatrick Hall, we'll go for a jog. And just to get you, people who are, I saw a lot of students who are expressing concern that they weren't able to get spots in the gym. We're starting to feel a little bit of cabin fever. So this is one way in which we can help out there. Please bring a mask and we'll make sure we maintain appropriate social distance, but all paces are welcome. So if you want to run, you want to be in a group, but you feel like you're slow, don't worry, we're going to stick together. All right, so what I would like you to do is take 3 minutes and work on problem 1. And as always, I have the Slack open, so if you want to ask questions, please feel free. Okay, so who would like to discuss what they got for this problem? I'd like to share their solution. Any guesses? Yes. B. So here's what's going on. The correct answer is in fact B, and here is why. So if we start out at the problem states that it ends at 730, right? So what's going on here is that first we call the this, which contains the base address of the class on the heap. So that's going to print 7 echo 0. Then we're going to print out the long unsigned integer and that address, and that's the same address on the data heap. Then we add 8 bytes for a long unsigned integer at 64 bits. So then we print out the double, so that's going to be 7E8. Then we add 4 more.
So
we print out the float and then the address.
We're considering going to salsas or mons. There's like rumors of the cops showing up or it being too full.
And then we add
or
4 more
like that.
to get the integer.
And not
and
getting a table. So like that's just
and all the
another
values
reason
that
like
were
why
passed
it wouldn't
in
be
main
like
are there. So the answer is B.
hello?
Okay. So let's keep going. All right, so from review from lecture 3, we started getting this idea of classes and how we're actually using classes to abstract a lot of this procedural programming from the user. And the objective is to kind of have a different type of computational thinking, where before you have this very procedural approach. We put something in the computer, we expect the computer to do something, and it often requires a lot of intermediate steps. We start out with this void pointer, then we cast it to a char star or an instar to take this void pointer, which is a structure, and we're adding the idea of data to get the first type of data structure. And so the idea of objects in real world operation, this drawing that I have here, this is a machine that was designed by Charles Babbage all the way back in 1837. And it was an analytical machine, and the goal was to perform all types of fundamental computation, addition, subtraction, multiplication, division, and various forms of calculus. And you can see that back then, the idea of the machine is going to take up, we have to use this building to be able to fit it. And as he's working on this, he has an assistant who's drawn here. Now, how many of you know of who Ada Lovelace is? Okay, several of you know who Ada Lovelace is. So Ada Lovelace is his assistant at the time, and she's writing up manuscripts, and she sees what he does and goes, hey, we can do so much more with this than just do math problems. And she's writing patterns, and when she writes this pattern as paper, it's widely considered to be the very first computer program. And in this same document, she includes this quote that I want to share with you, which really boils down to what it is that we're doing in this class and why we're starting out with classes to build towards data structures. So she realizes, hey, if we could break anything down from an object to some sort of mathematical operation, some sort of abstract science of operations, the computer might act upon other things besides numbers. Where objects, so she not only writes the first computer program, she's the first person to think object-oriented programming, whose mutual fundamental relations can be expressed by those abstract science of computers. Can we get these objects to interact with each other? So what we've done so far is we've built up from this fundamental set of operations, this procedural programming, and we're now trying to take these abstract science of operations and use classes to be able to relate real world objects with each other. So the first thing we're going to do is be able to convey the ideas in a way that's easy to read and understand. And the first thing we're going to do is something called a typedef, which stands for type definition. So do you have a question? Oh no, you're scratching your head, never mind. Okay, so the whole idea is, let's say you write some code and you have some floats and some doubles and you're trying to convey ideas, but ultimately what you want is somebody to be able to read your code and understand what it is you are trying to do. And so what we can do is we can create something called a typedef. What you're doing is you're not creating a new type. What you're doing is you're creating a new representation of that type. So for example, we are going to build a fundamental aggregated class with a class point, and then we'll have 2 points that represent a line. And so if we have a point, we can represent x and y as doubles on polar coordinates, as our Cartesian plane, excuse me. But if we want somebody to come through and understand what it is that we were talking about, we can actually use a type definition to say, well, how about we actually just call it coordinate? And this type def float coordinate is set up such that anytime someone types coordinate, the C++ compiler will replace it with a float. So what's going to happen is the user will read your code and say, oh, I know what they mean, coordinate, point, got it. That makes a lot of sense. But you're still conveying the same message to the computer. So let me show you an example. So I have this piece of code, typedef, and if you look at the top, I have typedef double coordinate. And here I have coordinate x equals 1.1 and coordinate y equals 3.7. And then I call standard cout, and I just print out a result. So what's actually going on here is the C++ compiler breaks it down into procedure. It says, okay, coordinate means double. All right, I'm going to allocate 2 64-bit double precision floating point values. And then I'm going to use this object-oriented approach to printing things out to create the 2 pointers and do the same thing like we did in Hello World. So what's going to happen when I run make typedef is it's just going to print out the coordinate. And so it makes sense. Now, if someone's reading your code here, they understand not just what you were trying to do, or understand that there's code there that does something, but what it is that your intention was. So this kind of idea of representing them in different ways becomes very useful for you as a programmer. So the next thing we can do is we can use these type definitions within a header file. Now, how many of you learned about header files in FunComp or Introduction? So a fair number of you. Okay, good. So I have this little note, this may be review, but I want to kind of go over this again to strengthen your understanding because you'll need to do this in Coding Challenge 2. So to this point, we've used libraries. In C, you did standard IO, C standard lib, and these are libraries that contains functions that you can implement. And so what we're going to be doing in this course is that we're going to be building our own libraries that you can implement throughout multiple programs by just including them. Now, in order to do this, we're going to create a header file. So a header file, we typically in C++, when we're building classes, before we get into templates, we're going to separate what are known as the method declarations into a .h file and a method definition into a .cpp file. I'm going to show you precisely how you should do that. So for the first thing you need to do in your header file is at the very top, you always do two things. IFNDF is short for if not defined. So if it's not defined, and then you put the name of the header file. So for example, say I have if not defined factorial h, then the next part is define it. I say, okay, define factorial h. So now you've defined your own header file, you have defined the method declarations within your own library. At the end of every header file, you should include this directive, end if. So just like anything else, it's ultimately an if statement. If this is not defined already as a library, define it as a library, then you put in your library, and at the end you put in end if. The reason I'm emphasizing this so much is because if you don't put in end if at the end, when it puts it on the instruction stack, it's going to think that all the code below it is also going to be part of the class. And so you're going to get these long compiler errors that don't seem to make much sense. So that's a good fundamental. If not defined, define, press enter a few times, then put in end if. All right, does anybody have any questions so far before I continue? Okay, let me check the Slack. I see we have a question. Since we did make file typedef, is typedef the name of the file? So this is a good question. So I'm going to be going over make files quite a bit today. But I'm going to show you at the very top that I called the file typedef. And I actually called the file typedef and compiled it, because the C++ compiler recognizes the difference between a file called typedef and the typedef keyword in the actual file itself. Does that address your question? Awesome. Okay, so let me go back here. And so one quick note, a common question I get, it's not required to do all caps, but it's considered good convention to do so, to put the definitions up there. So it's not factorial.h, it's factorial_h. Okay, so in a conventional class, what you're going to see us do is we're going to split up the .cpp and the .h files. Now, next lecture, in lecture 5, I'm going to tell you that you can't do that for certain types of classes. So I just want to let you know now that I might be contradicting myself in 48 hours. But what I want you to see is that this provides a way of being able to show the user the actual method declarations which are just the preconditions and postconditions, without showing them what's going on inside. If it works for them, it's good enough, right? So that's where we put the code into the .cpp file. So we use the if not defined, defined, and end if in the .h file. And in the .cpp file, what we're going to do is we are going to include the .h file. Yes? I'm sorry, can you speak up a little? You put it in the header one, yes. The header one only. And I'll show several examples of that. So the question was, where do we put it, where do we put the pound directives? So they all go in the header file only. Okay, any other questions? Okay, so I'm going to this is a basic example of a class header file. Let's see, if not defined, and I just say basic underscore h. And then pound define underscore h, and pound define basic underscore h. So now I've said if the basic library isn't defined, define it. And then I have the class, just like we did last week. I have private members, int, float, and double. I have an overloaded constructor that's public. And then I have 3 methods that are just get methods. So basically, because the methods are the members, the int, float, and double are private, I actually have to write a method in order to access them. And good practice is that you only write get methods or set methods, which are where you can update them, if you want them to be able to be accessed. If you don't want a user to be able to access that data while the object is constructed, don't create one. So that allows you for some data hiding. So another thing I want to point out that's really important, at the end of every class declaration, be sure to put a semicolon. You will get a lot of compiler errors if you don't do that. So in fact, what I'll give you like a very, I'll show you what I will do anytime I have to write a class. So if I have to write a class, we're just going to call it ds.h. So if not defined, and I would call it ds underscore h, and I would say pound define ds underscore h, and I'd say class ds, and then I would put the braces, I would put the semicolon, and then I put end if. Every time I write a class, that's the first thing I do. So that way I make sure that it compiles correctly. Okay, so the next thing I want to do is talk about class definitions. This is what's going on in the .cpp file. So when you have a class declaration, that means that you say what the methods, I'm sorry, when you have a method declaration, you're saying what the method's name is, so like get x, and then you have the preconditions, which are what are the inputs, and then the postconditions are the outputs. So we saw that, and it had a semicolon, and that's all it was. In the .cpp file, you have all the same information, but you also have to indicate which class you're referring to. And the reason why is because you can have multiple class declarations in the same header file. So you want to be able to relate which one is which. So the way you will set it up is you'll say the return type, just like you would do in the .h file, but then you do this class name : Then you have the same method name and the same variables. So I give 2 examples here. In the .h file that I'll show you in a moment at this point, I have a method get x, and all it says is get x, like so, within the class declaration. In the class definition, it also says coordinate because it's returning a type. So here in the .cpp file, I put that in front of that, and then I'm actually going to define it there of what I actually want it to do. And I do the same thing with point, where it's not returning anything. point's the class, set x is the method name, and coordinate in x is bringing in that value that I'm going to use to update. So class constructors in the .h and .cpp, there's one key difference, is that in both the .h and .cpp, constructors do not have a return type because the return type is the object itself. So for a default constructor, if you don't write a constructor at all, the C++ compiler makes it for you. But it's good practice to do it. So it initializes each data member, so it'll actually do that exact same thing that we've been discussing, where it'll allocate a pointer, allocate it in the exact same order on the data heap, just as we've seen so far with the nodes that we constructed earlier when we did that last week. The other crucial thing is if you implement any constructor for your class, the compiler will not supply a default constructor. So if you create a constructor, but you try to create a default constructor, the compiler's going to go, wait a minute, you promised me I wouldn't need to do this, and it'll shut the program down. All right, so kind of the same thing in the .h file. We had point, where we have a constructor with two inputs, coordinate x and coordinate y. We don't have any return type, and we've worked on that before. In the .cpp file, it's the exact same thing. Said with the, I have the class point, : there, and then I have the member initialization list afterwards. So you would put the member initialization list in the .cpp file. So the method declarations are there to say, all right, this is what this class can do, and this is what the class contains with the private members. And in the .cpp file, we describe what actually is done when we call those methods. Okay, and I've gone over this already with the return type, but I just want to emphasize again that in the .h file, this would be a normal method. We see that I have point : there in between the return type and the method name. So a very common student mistake when they're first getting used to this is they'll put point : over here like this and not have that. So just make sure that it goes return type, class name, method name. Okay, before I go into code examples, does anybody have any questions? Okay, so first I would like to show you the class declaration for point.h. So what I have here is I have if not defined and define, I have the IO stream, and I have a typedef float coordinate. So what happens is anywhere that I have pound include point.h, I can also call coordinate because it's also included. So from there, I have the class point, and I have two private members, coordinate x and coordinate y. For public, these are my method declarations. I declare that I can get x. I declare that I get y. Well, how do you do that? All right, well, I'll define it in the .cpp file. So here I have a default constructor, point. I have an overloaded constructor that takes in two coordinates. And then I have these get and set methods. So get, which we'll see in point.cpp, has the ability to return the private member x, and the same thing for y. Set x and set y, I will take these in. and I can update the values. And then I have a method print point. And again, you see that I'm emphasizing, please remember to put the semicolon there. So for the .cpp file, I have my default constructor. So if I create a point object, it sets the default floats as 0. The other thing I want to point out is this pound include. So the .cpp file, excuse me, should contain pound include the .h file. So in my folder here that I have on GitHub, when I do ls, you'll see that I have the folders just like you saw in lab 1. So I have all the files for header files in the include library here. And then I would have all the other source files here in .cpp. So it allows me to say, all right, if I include .h, I can include this in all these other files. So since src and include are not the same folder, I have to go up one level, then go into include and go into point. So that's why it's that specific way. And so that's something you'll need to do in your coding challenges once we introduce classes from coding challenge 2 on. From here, I also have a overloaded constructor. You see in both cases, I have the member initialization lists. And then here, because I have point : : this allows me to just say return X, because I'm indicating that it's a point object and therefore it should have access to the private members. Does that make sense? All right, good. Same thing with get Y, and then set Y, I can bring in coordinate X in, like so, and I can do the same thing with set Y. So for print point, what I'm doing here is I am just printing out the coordinates. I'm putting in braces and X and Y, and it'll print out the values that are private to that specific point. I see someone's typing. I'll address the question in a second. So then if you want to review it, I have these animations that describe everything that I just mentioned here. So in point example, okay, so here's the question. Can you repeat what a constructor is and which is the constructor in this example? All right, let me go back a few slides. The constructors are the ones that don't return anything because it's actually creating a point object itself. So the first one here is the default constructor. And then this one is the overloaded constructor. And so when I show you in pointExample.cpp, when we actually create these objects, I'm going to show you how it is that we call all of them. And then I'll follow back up and see if that addressed your question. And so I see there's another question coming. I'll address it in a second when it's typed. In the meantime, what I want to do is I want to show you what's going on in pointExample.cpp. In this specific file, this is how you call a default constructor. In a few slides, I'm going to say, whatever you do, don't do this. Whatever you do, don't put the empty braces like that after it. And I'm going to show you why. But that is the default constructor. You have the name of the class and the variable name that you wish. Okay, so here's another question. For the set methods, do we not need to call the variables by reference? I'm going to get into that later. But yes, you eventually will need to. All right, so point 1 is, and then I call the method for print point. Since it calls the default constructor, it will call 0, 0. For here, for point 1, I can change the coordinates here using set X and set Y. And then I'm going to print it again, and it's going to give me 3.1 and 6.2. Then I have a second constructor for point where I have negative 1.1 and 5.3, and I'm going to print that out as well. So here, if I go back up and I do make point example, we will see that exactly what we predicted was going to print out did. All right, does anybody have any other questions? Right, so here again, I'm going through the same thing, default constructor, class method, set methods, coordinate, like so. Right, so in make point bad.cpp, this is the exact same code, except I made that mistake I told you I was going to allude to. Even I have deliberate logic error here. What this is going to try to do, it's going to try to create a class of point and then add the parentheses afterward. Point parentheses, not point. And so it's going to give you a bizarre looking compiler error. I'm going to show it to you so you know how to address it. Make point bad, and you see these 4 errors. Request for member print point in point 1, which is of non-class type point parentheses. So what that's actually saying is that you tried creating a class point parentheses, not class point. Point parentheses is not defined, and as a result, you're trying to create of an object of that point, of a non-class type. So that's why we want to be careful when using default constructors to call it like I have here. Does that make sense to everybody? All right, so the next thing we want to build on is class aggregation. What happens when class objects are private members of other class objects? So we previously created a class called point. And in geometry, 2 points make up a line. So now we can actually represent real world objects because we've related these mathematical and computing operations, these floating points, to a point, and then I can build 2 points into a line. So now we're going from procedural, mathematical to ideas, to these objects. And this is what is known as class aggregation. So this will be something that we'll revisit a lot. So for example, a stack aggregates a singly linked list. That's something we'll discuss later this semester. Queue aggregates a doubly linked list. We're going to see that a display tree aggregates a binary search tree. A graph aggregates a dynamic array. Same thing with a hash table. We're going to see this concept come up over and over again. What happens when a class has private members that is also a class that we defined? So what I want to show you now is the line.h file. And in the line.h file, the first thing I want to show you is that after defining the file, that I've included point.h. So by including point.h, this allows me to be able to call the methods, the public methods of the point class for a point object. I have 2 point objects here, private origin and destination. And then I have 3 different types of constructors here. So I have a default constructor, and then I have 2 overloaded constructors. The first overloaded constructor is if I have 2 points. The other overloaded constructor is if I have 4 coordinates. So I have coordinate x, origin x, and origin y, and then coordinate destination x and destination y. So I can create as many constructors as I want, provided that I can take that information and turn it into a valid line. So that's something that may become useful when you're working on various projects. The other thing I point out in the slides is that the point.h, because it's in the same folder, you don't need to add that / include. It's already there. Since it's in the same folder, you can do that just fine. So here we have the private members that's aggregated from point. We have the default constructor, overloaded constructors 1 and 2. And then I have get methods. And then I have 2 methods operating on the private members. So I have one called get slope, and I have one called print line. So from there, if we want to build a constructor in the .cpp file, we can use those in the member initialization list. So for example, with line, I have my 2 inputs to the default the overloaded constructor, and the 2 objects that are allocated on the data heap, origin and destination, are actually 4 floats, but we can allocate them like this. Does everybody see that? So this allows us to be able to allocate it in different ways. So here's the other constructor. And something you're allowed to do is you're allowed to call a constructor inside a member initialization list. So what's actually going on there is I am creating a point object that I'm going to allocate on the data heap that is origin. And then to get to destination, I'll allocate another point object and allocate it there as well. All right, so in line.cpp, where I have the method definitions, you see that I have the file, line.h, point include, so I get into the right folder. And then I have the default constructor, and you see here that I have 0.00, 0.00, that I can call these constructors here. Then I have point and point for destination there. So I can take previously constructed points and put them in there, or I could actually take in 4 coordinates and construct 2-point objects and allocate them that way. Okay, does anybody have any questions about that? All right, so now the next thing is the methods. So you see we're doing the same thing. Yes, you have a question? Sure. Yes, so the question is the default constructor have the default values for the private members of the method? And the answer is yes. If you just have it, if you did it like this, so let's go back here. If you just left these blank, took that out, it would call the default constructor for point. It would do the exact same thing that I just had there. It would create a point of 0, 0. The one thing to bear in mind, to go back a few slides, if you don't create a default constructor, the C++ compiler will not create one for you, so you won't be able to do that. Did that address your question? No, no, it's not for private members. It can be, it's also for public members. Yes? No, nothing to apologize for. I've included it, you do not have to. I have included it there to reinforce to students that it is possible that you can do that. But you could cut those out as I have shown on the screen. But you could, if you wanted the default line to be other things, like for some reason, we wanted this to be 1010 and 2020, we could do that. Did that address your question? Awesome. Let me check the Slack. Okay, I don't see anything in the Slack. So there's the get methods. And again, we have line, and it can return the private members. Get slope. Here we have the private members, and now it's calling the get methods of point. So destin.getX and destin.getY, origin.getX and origin.getY. Because X and Y are private members of the point, I cannot do this. I can't do that because X is private. We're hiding that data. The only time somebody should be able to access private members of a class is if you have a get method, something like this. So that's why I have to do it this specific way. And then last but certainly not least, in line print line, I can actually call print point. That'll print the first point, and then I put in a comma, and then I call the second print point. And so I can print 2 points to represent the origin and destination of the line to the user. So what I would like to do next is I want to combine concepts and show what's actually going on at different levels of abstraction. So here we have object-oriented, but we're now doing the same thing on the stack and the heap all the way down at the architectural level and showing it how it works as a procedure. And so Simran, this should hopefully clarify the question you had a little earlier. So first what I do is we call main, and that creates a copy of all the code onto the instruction stack. The next thing that happens is I'm going to call the default constructor here, point1. And so what's going to happen is the first thing it'll do is it'll make a copy of the constructor onto the instruction stack, like so. And then it's going to create a register, which is this pointer for that particular object. And now it's calling the default constructors for point. So what's going to happen is it's going to create point x, y, and then I'm going to create point 2. Point 2, it's going to do the same thing. It'll make a copy of the constructor onto the instruction stack. Then it's going to create room for 1.1 and then 5.3. So now I'm going to call the default constructor for line. So line aggregates point. So how does this work on the stack? So it's going to call the default constructor, and it's going to create a this pointer for the line 1, and then it's going to create the first point. So it'll say, all right, give me point1.x, point1.x, and then point1.y, and it'll give me point2.x and point2.y. Or that would be, we could also call that origin and destination. And since it's default constructors, it'll put zeros there. And then you'll see down here, I have line 2, point 1 and point 2. And I'm doing the same thing. I'm creating a this pointer. But now I'm passing these 2 points, and I'm creating a copy of them. And so now it's going to be 0 and 0. But then the second one's going to be 1.1 and 5.3. Does everybody see how that works? Awesome. All right, so what I would like you to do is problems 2 through 4, please work on those, and we'll address this back in 5 minutes. And the objective of these problems, as you're starting to get them out, is to work through, understand how classes operate, and how the underlying types contribute to what comes out. So who wants to share with me their solution for number 2? Who thinks they got the right answer? Everyone got it wrong. Okay, so anyone want to take a guess? Got to pick on somebody. Yes. C. All right, so C is the correct answer. I think it's the correct answer. Yes, C is the correct answer. So what was the interesting thing going on with class A? Why did it print out 1 instead of 1.5? Yes. Yeah, it's an integer. So what happens with an integer is if you get a decimal, it just lops off the remainder and it'll give you the result. So that's why it prints out 1, and then 2.667 is the result for when you print it out with a double. All right, so what about number 3? So number 3, we have this class A, and then we have class B, which aggregates class A, and then it asks us to print out 1 and 4.5, and then it calls func. So func was A minus B, and so it allocates 4 and 1.5 here. And then when we call B, you see that it calls a overloaded constructor where it takes in the 2 doubles and creates an object of A. And so it's going to print out 4 minus 1.5. So it's going to print out 2.5. I'm sorry, that's plus 5. I apologize. Okay, so what about 4? This was a little more complicated one. So I have a aggregated class A and B aggregates A. In the current code, there's a combination of code in main and in class method in order to print the values in A that are private members of class B. So here we see that we have get methods, get A and get B, and I have a constructor that takes in 2 integers. And then I have 2 methods private that aggregate class A, A1 and A2. And what's going to happen is I create a constructor, so we have quite a couple comments in the chat. It was D. Let me check the other thing in the chat. So what's going on here is I ask for a class method which would go here if necessary, and if there's something we need to do in main. So what was the answer? Anybody want to share what the answer is? Anyone else? I'll pick you over there all the way in the blue. Yes. You have D? So D is the correct answer. Now let's go over why. So the reason why A is wrong is because here I have standard C out, get A and get B, get A and get B, and I call it B1 print vals. And the issue here is that when we call D here, we print vals, we get the private members, and we call the get methods to obtain those in print vals. Does that make sense? And then, yeah, that was the correct answer. So then in main, I call the private methods that I've created in main. Okay, Yassine got it right, very good. All right, so does everybody understand why D is correct? All right, see a big thumbs up in the back. All right, so the next thing I want to do is I want to go over how to build classes and aggregated classes in a makefile. So first I want to show you the makefile, then I'm going to show you this animation on here to show you the steps on how you can build this on your own. So first, in the makefile, typedef, I've got point example. When I make line example, the first thing I do is I have to create 3 objects. I got to create an object for point.o, which will create and compile the point class. The second one is going to be the line class, so I have line.o. And notice how, just like you did in lab 1, we have the source for line.cpp, and I want to put them in the object files by using the -o $@. Then line example is the CPP file that contains the actual code that I'm going to run, that uses the class to perform the message passing. Once I've done that, then I create this variable line examples. And you can see that I'm putting all the object files here. So as you get larger and larger projects, the benefit of defining the object variable name hopefully becomes clearer, in that you can put all the objects there, and then instead of having to copy and paste them here and here, you can just use the variable name there. Does that make sense so far? So what I would like to show you now is going through the animation to show you how I create this. So first I have point.o, and you'll see what happens is I take the source, which contains the class definition, and point.h, which includes the class declaration, and I compile those to make objects point.o. Then I do the same thing with line.o. Now notice here that I have a little arrow because we include point.h in the line declaration. So then line.h and line.cpp then create the object file for line.o. Then what happens in line example.cpp, I have pound include line.h. When I have pound include line.h, it also includes point.h because point.h is inside line.h. And inside of point.h, I have typedef coordinate. So everything is included in that point example.cpp. And I use that to build the last object file. So then what I do is this takes all of those object files and creates an executable. The executable is what you run, of course, when you complete the program. And then that line of code there automatically runs it. So when I'm doing class, I've included commands there. So when I run the executable, I don't have to waste more of your time by performing another command. So it runs it automatically for me, and therefore I can use that to demo. So if you wanted to build it that way, this would be the perfect way to aggregate classes in order to build all of the objects that you need. So it matches your code to what's going on in the machine. Then you take all those objects and it turns it into an executable, so you know exactly how to execute the program, and then you're able to run your code. Does anybody have any questions about what we've done so far with classes, what we've done so far in terms of makefiles, aggregation? It's kind of a lot, so if you have any questions, please don't hesitate to ask. Okay, nothing in the classroom. Let me check the Slack. Okay, we have one question in the Slack. The $@ in the makefile here. So we briefly visited this in lab 1, but what's going on here, to refresh, is that I'm saying that I'm taking these compiler flags, and I'm taking this .cpp file, and I'm turning it into an object file, and the $@ relates to this right here. So what that says is I want to take the line example.cpp that's in the source folder, create an object file called lineexample.o, and place it in the object folder. Did that address your question? Awesome. Okay, so next thing I want to discuss is pound define directives. We've discussed these briefly, but I want to show you an alternative that's going to be helping us in C++. So when we have pound define directives, we don't have to just use them to define cout for standard cout and endl for standard endl. We can actually use this to replace, if we have pound define pi, and I can say 3.1415, right? So anywhere that I have uppercase pi in the code, the compiler takes it as its directive to replace it with 3.1415. The challenge is, what happens when you try to use that in C++ compilers? Sometimes this causes an issue when you're trying to replace numbers with compiler directives. So, I'm sorry, you can use these to get around global variables. So one of the drawbacks of global variables, I'm sure you heard in previous courses, that while it's good to know what they are, sometimes they're considered bad practice. And the reason why, if you have an aggregated global variable, it gets copied. And you have copies, they conflict, the compiler says, what are you doing? And then you want to scream and say, I only typed it once, what are you doing? So we want to come up with a different way to get around these issues. And so to give you an example, let's say I have a file, I'm creating some code fact header bad. So this is deliberately wrong. And inside fact bad.h, I'm trying to create something for factorials. When we get into dynamic programming, we'll learn more about the values of these particular numbers. But what's going on here is I've created some variables that can be aggregated. And what happens is, in fact.cpp, it makes another copy. So when it puts all this together, there's multiple copies of the same variable. So what ends up happening is this code won't compile, even though you didn't intend it to have duplicates. So what we do instead is we have pound define. So pound define just means that the compiler sees whenever you have it in there, it updates your code. It doesn't allocate a specific register to contain that value. That's the difference between a compiler directive and a global variable. So that saves the duplicates and allows you to be able to compile. But there's another thing we can do. So C++ comes along. We are thinking maybe we want to have some sort of global variable, but we don't want to make duplicates. So what is introduced is a keyword called const, which is short for constant. And the whole idea is that the const variable, once you define it, it's only been defined once and it cannot be changed. So for example, I want to do this pi thing. It's in C, this procedural programming. I can do pound define pi 3.14159. If I still want it to have a specific type, so for example, I want to be very strict with integers, long unsigned integers, floats, doubles. We need to be very careful, like we're working in aerospace. We don't want to inadvertently blow up our spaceship, right? So I can say, all right, const float, this variable name equals this particular value. It allows me to give more structure, or I'm sorry, more control of the structure of that particular piece of data. So what's going on here, I have const double pi equals 3.14159 with a semicolon. I made a little note here. That's the other difference there. And what that allows me to do is it says, all right, anytime I encounter this, it is by default a double. And if I'm using comparisons, I need to be very careful to make sure that that's preserved. And so there's a lot of benefits of const. Does anybody have any questions before I continue? All right, so in object-oriented C++, we prefer const to define. That's the reason we can explicitly state the type. It gives us more control over the type of data structure. We can use variable scoping rules. So basically, we don't want somebody to define another variable with that name. That allows us to be able to do it that way. So one of the production quality compilation flags that we use to preserve this coding practice is wshadow. So if you have a variable int I outside of a while loop, and you have int I inside of that while loop, the one inside of the while loop is known as shadowing the one that's outside. So we are strictly enforcing that we can't have shadowed variables. And const allows us to be able to do that. Likewise, as you, for those of you who were in lab on Monday, you learned about GDB debugging. You can't see the value of a pound define directive when you're using GDB. So GDB is the debugger, but you can figure out what const is. This allows you to be able to do improved and more efficient troubleshooting. All right, so first what I want to do is show you a basic piece of code. And this const.cpp, I'm using pound define directives to say cout and endl. And anytime an encounters cout and endl, to replace it with standard cout and standard endl. But now I have a const global variable, like I showed in the slides. You can see that I don't have semicolons here, and I do have a semicolon here. So the difference is I'm now saying this is the type of data that I want, not just the value, but the data type. I have two function declarations for circle area, and I'm passing a value of a double radius. And in main, what I'm going to do is I'm going to first just print out the radius and the value of pi. And then in this method, I'm going to call circle area and print out the area, and then I'm going to print out the circumference. In those functions that I'm going to show you down below, it's actually going to use the const variable pi, as well as the variable that I've passed, pi times radius to get the area. And then I use pi times radius to get the circumference. So I can ensure that no one's trying to call something else pi when we're doing this. So if I call make const, clear, it'll print out the radius, the value of pi. We see that prints out exactly that value, and then it prints out the area and the circumference of the circle. Okay, does anybody have any questions on this so far? All right, so the next thing, is this idea of function overloading. So in C++, in C, if you call a function by a name, you cannot call any other function by that name, period. In C++, you can, and I believe those of you in Fundamentals of Computing, you learned this in the last 2 weeks of the semester. If you took my intro class, you learned it there, that you can actually overload the function provided you have different preconditions. And I'm going to show you several examples of this. And the reason why you want to do this is it might be logical to have that function be named the same thing, like print value, very simple example. And the value, but we can pass different types using function overloading. If the preconditions are the same, you can't return a different postcondition. And what I mean by that is if I said print x, actually I have several examples on the next slide, I believe. Yes, so good example. If I have a function called print me, I can call int temp x or standard string temp x, and that's a valid example of function overloading, because inside I can print the string or the int based on what the function is. So bad examples, if it's the same precondition, the compiler can't really tell. And this versus call by reference has some issues. Does anybody have any theories as to why passing it by value as opposed to call by reference might cause a problem? Yes, in the back. Absolutely right. So the crucial thing is that when I am calling by reference, I can change the value, and the value is updated in the calling function, whether it's main or somewhere else. Here, any change to temp X that we make goes away the moment we go out of scope. And so I have a function overloading example where I have string, int, and string. So let me bring up the code. There we go. And so in the first one, I just have a string, and I say string s is equal to s. In the second one, I have I, and it prints I. In the third one, I have string s and I, and I can print both of them out. And so when I run make func over, we're going to see that here I created hello world as the string and 25 is the int. So it should print hello world, 25, and then hello world and 25 in the third call. We see that's exactly what happened. And so C++, that's permitted. And what I want to show you here is this example where I have an integer, a const int, and then another example where we call by reference. So we have, if it's an integer and I make a change with int I plus 2, that change is preserved. Const means the value can't be changed. So here I have I plus 2, and that doesn't work. And if I have int ampersand I, so I'm calling by reference, and I say I plus 2, that change is preserved. And so what happens is it can't tell the difference, the compiler cannot tell the difference between them. So what ends up happening is it gives you some ambiguous results. So this code I showed you is in something called make ambig or ambig.cpp. And you see that the errors show redefinition of print int, and it says previously declared here, assignment of read-only parameters. So I have the const value that's being updated. Does that make sense? Okay, and we see const used in class objects. So the use of const allows you to control whether or not something can be changed. Furthermore, and this addresses Carlos' question from earlier, if you want to be able to pass created values such as 1.1, -32, and pass it to a class, you want to do const, the type, and then call by reference. And that allows you to be able to ensure that it doesn't get changed, but only pass a pointer to the temporary object. Okay, don't change the data members or const. All right, so what I've done here is we have this, we can define class methods as const. And so when you do this, this will be the remainder of the problems in Sakai. And so what's going on here is that anything that does not change a private member of a class, you should call the method as const. So here, get origin I call const, get destin I call const, get slope. This doesn't change any of the private values, so it's const. But you'll see that the set methods are not const. And so the way you do const is you have the method name, and then you have const, and then the brace afterwards. And so the goal there is you can say that a const version of a line, you've declared a line, and you say cannot change it, it is const. That means that a const version of that object can call that method. Does that make sense? So we see that const, that set x and set y are not defined as const. So if I have a line that is const and I try calling that method, it'll throw a compiler error. So that's your way of informing, providing more data hiding about what is allowed to be done and what's not allowed to be done. And so I think it's the time for the problems. All right, I'm going to skip these because you have the opportunity to do these problems. Okay, so please do problems 5 and 6. And so what I want you to do, and I'll go over this again as you're working on them, is we have all of these methods here for point or line. So let me give you an example as you're working on it. So constructors should not be defined as const. So these three would not be changed. And here I have get origin and get destination. So I would want a const point, a constant line, to be able to call that. So you would go through, and there's going to be a problem like this on the exam as well, where you have to identify which methods may be called and which ones can't be. So float get slope, this one should be const too, because it doesn't change anything. It gets a result based on an operation that gets the information but doesn't change it. And then likewise with print line, I would call it const as well. Now the crucial thing as you're working on it, the .h and the .cpp method declarations have to match as well. So I have to go through here and I have to say this one's const for get origin, get destin, get slope, and print line, and that all works. And now we'll do the same thing for point.h and point.cpp. So in point.cpp, my constructors aren't named const. I can just get the value, so I'm not changing anything. And this is the same type of thing that you'll see in the problems 5 and 6. Set x and set y are updated, so therefore they are not const. And then print point would be const. And I'd want to do the same thing in point h for consistency as well. Okay, so problem 5. Which ones of these should, so I've given several that I've said should be const. We'll go through these two problems and this will be we'll wrap up lecture. Which of these should be const and which one shouldn't be const? So here I have a constructor. Should this be const, yes or no? A lot of no's, very good. We have a get name. Should this be const? A lot of yeses. Get age also? What about set name? Set name shouldn't be. And so I kind of breezed over it, but the happy birthday will contain a method that prints out happy birthday and then increments the private member of age by 1. So we don't want that one either. So that's B and C are the correct answers for 5. And for number 6, come on, there you go. For the last thing, it's going through and it's going to ask you which ones should be changed to const. So should we name this as const? Okay, a lot of no's, very good. What about set x? Okay, nope, very good. Get y? Very good. Sum returns the sum of x and y, a lot of yeses, that's absolutely right. And what about swap? Very good, it's not the case. So we would have that case, the answer is C and D. All right, does anybody have any last second questions before I dismiss? All right, on that note, it's 2 o'clock and you're free to go.